Next, we have Bharat from Georgia Tech.
Hi, my name is Bharat Ravi. I'm a master's student at Georgia Tech, working with Professor Nick Feimster. And my talk is on our research on how we try to use BGP traffic engineering at a service or an application level. And this is what we called joint network and content routing. So to give you some context, our initial approach was to try to optimize performance for the common online services we have today, which are the usual suspects. We have a Google search, Amazon shopping, which are pretty massive in the terms of number of users that they have and growing, and in pretty competitive environments. This is one where stuff like latencies at which you deliver content to your users really matters. So to optimize this content delivery to users, focus on throughput, latency, or jitter, there are two typical ways content providers might do this. The first is network routing, where you try to find better alternate routes to your customers. And the second is content routing, where you try to push your content closer to users. So we use these terms, network and content routing. So let me first define what exactly we mean by them. So network routing is something everyone here is very familiar with. The problem is essentially one of evaluating and using better routes to content if available. And this is typically through BGP traffic engineering. So here I should also clarify by network routes, I mean a hop of ASPs, ASS or ISPs. So as the diagram shows on a crude level, you have clients or a set of prefixes on one end and a content provider's POP at the other. And you have various alternate paths. And you use traffic engineering methods to decide which set of ASS or ISPs you want to send your traffic through. And there are typical methods for this. In the long term, you might try to find new peers or better upstream connection, or try to set up a new POP. In the short term, you have the standard local pref or selective route announcement techniques and various others. So what is content routing? So the problem here is a little different. Instead of a single content provider, you now have the same content replicated or available at multiple locations, which is with what we call replicas. And the problem now is one of directing every client to the replica that is most ideal to it. Perhaps the replica that has the least latency for the client, or the replica that costs least for the content provider. And this is what we call global traffic management, or GTM. So as the diagram shows, you have a client request coming in, and you have a GTM system that could be implemented through various methods, probably something like DNS or through HTTP redirects. And this system or this interconnect somehow decides which replica is ideal to this client and redirects that request to the said replica. So how is this done? Typical redirect methods are using DNS to redirect a client request to something that's geographically closer to it. HTTP redirects for more high-level applications. And the factors that you redirect based on are stuff like latency and throughput, or how much load your servers are facing, or how much cost it takes to actually handle a request at a particular server. So let's consider a typical scenario. You have three replicas, replica A, C, and the one in black, which is eventually the chosen replica. You have a client or a set of prefixes that's making a request going to a GTM system. So typically how this GTM system or a load balancer works is that it redirects some small portion of the client request to each of these replicas and evaluates performance. And depending on which of these performance results are the best, it's going to redirect the client to the chosen replica, which is the one in black. Now, network operators presumably at that chosen replica are going to be seeing this incoming heavy traffic through this certain prefix. And now their job is one of optimizing network routes for this heavy traffic. But there is a potential problem here. The reality actually looks something like that. So you actually have multiple routes to each of these replicas, but the GTM system actually only sees the current route, which is what we call the default route. And these are the ones, the blue routes highlighted in bold. So since a GTM is a service level application or an application level service, it's only going to see the routes that are being optimized already by the network providers. So all measurements or all redirects and evaluations that is performed are over this single route. And network routing or traffic engineering happens at a stage below this GTM system, wherein you see this traffic incoming and then you try to choose between optimal routes. So what if there's a better choice that the GTM system does not see because the routes don't exist? Say network operators at replica A never see heavy traffic, so they never find a reason to optimize for that particular set of prefixes. So there might be an overall better choice to a different replica that this GTM system might be missing out, simply because it does not have the capability, being an application level service. So the problem is, can we do better? On one hand, you have content routing with GTM systems that have little visibility or control of these network paths and measures performance only against the paths given to it. On the other hand, you have network routing where you guys have a lot of tools to explore these paths and select between them, but typically you don't see the application level service at an abstract level. So the question we asked is, can we give these BGP traffic engineering capabilities of what we call network routing to this higher level GTM service? So our solution is what we call joint routing. So the left hand shows what the reality is. Which is you have a GTM interconnect with a number of replicas, with each having a number of routes going to it. And the routes in bold are the ones that the GTM system eventually sees. Instead, we use an abstraction. So at replica A, you have two routes going through it, route 1 and route 2. Let's provide the GTM system a notion of virtual replicas, which are actually combinations of replicas and routes. So what we want to do is give the GTM system a view of replicas A1 and A2, which are actually the same physical replica, but A1 is replica A with route 1, and A2 is replica A with route 2. So this is the view that we would like to give the application level service. And this interconnect is our joint content and network routing system. So using virtual replicas, the method that we use is, first of all, do a brute force exhaustive search, where we enumerate all possible network routes at all possible replicas, evaluate performance of various client prefixes over each of these routes, and then we use existing GTM methods like DNS or HTTP redirects to select between these virtual replicas instead. And we call this joint because these steps are performed by a single system. So our goal when we started out was, okay, you can do this. What gains does this offer? So to do this, we established a test bed and actually evaluated what can be done with this. So our setup looked something like this. We have 5 replicas, which are simply 5 servers in various universities around the country. And for clients, we used an open test bed called Planet Lab with nodes around the world, although they are a larger percentage of these nodes are in the US. And at each replica, we evaluated around 250 alternate routes to each of these prefixes. So as the diagram shows you, we have around 200 clients, 250 into 5, one for each of the replica routes, and 5 replicas. So how do we actually explore these 250 different routes? The techniques that are typically available are things like setting local preferences or weights or tunnel egress for egress route selection, and stuff like selective path announcements or using community attributes, community peering arrangements, or AS path prepending to affect from where traffic is coming to you, which is ingress route selection. However, our setup does not permit using these, and let me explain why. So this is what it looks like. On one hand, we have our clients, which is a Planet Lab node. On the other end, we have a replica, which sits within a research AS. And this research AS speaks to the outside world using a university AS. Now, because this is a research system and things are largely in flux, attributes like local preferences or weights are ignored by the university AS because it does not want the trouble of actually dealing with that flux. So how does this research AS control ASS and ISPs multiple hops down the line to select between routes? Since it does not peer directly, we had to resort to using AS path poisoning and focusing only on ingress routes. So poisoning is typically a method of forcing a route around a certain AS. And the example highlighted here is where I have a certain server sitting in, say, ISP A. My clients sit in ISP B, and they talk to me by routing packets through ISP X. Whereas I would actually like to receive packets through ISP Y for various reasons. Now, how do I cut X out of the loop? I make an announcement of my prefix by adding x's AS number to the AS path. X, upon receiving this announcement, thinks that there is a loop, and it's not going to propagate this announcement to B. So now when B has to send a packet, it has no other choice but to send it through Y. So this is typical poisoning that we use. The measurements that we perform with this method, for every client, evaluate performance at every virtual replica, which means every replica root combination again. And we evaluate latency using ping, throughput and jitter with iperf. And we use traceroute to actually determine the topology of ASs, to determine which ASs to poison. And at each replica, we did around 1.5 million pings, around 500,000 iperf measurements. And this was over a period of around 3 months. So we started with, we had 5 replicas at hand. And for a baseline, we started with a single best replica, by which I mean the single replica that is actually best for the largest percentage of clients. It has the lowest RTT latency for the largest number of clients, say. With this best replica, we found an average RTT of around 107 milliseconds. Next, we added network routing to the setup, where at this one replica, you choose between various available routes to you by using poisoning. With this, we found an approximately 4% reduction in RTT. And now we tried out content routing, which means we added in 5 replicas. We didn't choose between network paths. Every client simply chose the replica that was ideal to it. With this, we found a much more drastic reduction of around 16.7% in our setup. So finally, we tried out joint routing, where we do both, as I explained. With this, we found a 20.4% reduction. So joint routing, at least in our setup, seemed to yield a 3.7 percentage point RTT improvement over content routing. For throughput and jitter, we saw similar improvements. For throughput, joint routing improves by around 3%. For jitter, it improves it by around 6% over content routing. And looking at where these improvements come from, we actually see that joint routing gives marginal improvement over content routing. And by marginal, we really mean this little incremental bump over content routing that this graph highlights. So the y-axis numbers are off because the y-axis is not a relative gain, which means it's off by a factor of 10. But the important thing to note here is that as we increase the number of replicas, both joint routing and content routing start growing in benefits because you now have more replicas to choose from. But this margin or this incremental bump does not really disappear. So it seems to stay as you add replicas. And where does this improvement actually come from? Out of 200 clients, we saw that 7% of clients actually moved to a different replica, or most importantly, a different virtual replica, which is a combination of root and replica again. So how much chaos does this cause? 200 clients, 5 replicas, 250 roots seems like a tremendously explosive amount. So how many poisons do we actually need to announce? We found that it's not as explosive as it seems to be. With around 5 poison announcements at every replica, we get around 60% of the maximum possible improvement, around 60% of that 3.7 incremental gain. With 7 or 8 poison announcements, we get almost the complete 3.7 gain. So although these are quite a few announcements, it's not as explosive as the multiplicative number would have you believe. So this is a summary of the results. We see some incremental gains over content routing, and with a relatively few number of poison announcements, we get around 60% of the maximum possible improvement. So what next? These are the questions that we would like to ask Nanog. First of all, ours is clearly a research setup, which is nowhere close to the real world. So how do we make this practical? Is something like this already attempted or considered? Will it even work in the real world? For example, we see 250 routes because we use AS path poisoning. What is typical route diversity you guys see in your networks while choosing between ingress or egress routes? AS path poisoning, for example, is really not the ideal way to do this. What are alternative methods? Or even better, what are more realistic test beds we could use where we could get a better picture of what happens in the real world? And finally, when is joint routing actually useful? So we evaluated joint routing. We found that in our test bed, it gives some amount of incremental improvement. What use cases actually find this useful? And more importantly, what do improvements actually look like in a real world setting? Is joint routing actually worth it? So these are our asks from Nanog. So if you have answers to any of these questions, if you could tell us why this would work or why this couldn't work, or even better, if you would like to give us a research testbed where we can run experiments, please do come talk to me at the break. Or you can also email us at any of these things. So if you have any questions or feedback for us, I'd be glad to listen.
We have time for questions.
Hi, I'm Patrick from Akamai. I know you guys are getting bored of me. Tough shit. Moving on. You have a single stub AS, and you're poisoning something outbound through a couple of upstream ASs. Most networks are slightly more complex than that. So first of all, by poisoning one path, you've now removed a backup path, which is the reason most people have multiple upstreams. Second of all, you've optimized a single path from a client to a piece of content on your network, whereas the graph of all source and destination points, especially for a transit network, is far richer than this. So your 3.7% improvement on the best possible case scenario where you have a stub network and two upstreams seems like a very, very low benefit for what could be a complex and massive disaster for other things. So your real world question, I mean, I don't know the answer to that, even though, to be honest, I do this for a living. It doesn't sound like it's a good idea, at least not for poisoning. Perhaps for prepending, you might have a different case, but even then you run into things like people may not want you to prepend because they're business relationships. Forcing it from transit A to transit B suddenly costs them more. And so there are reasons why these kind of things are not done. And that's one of the main reasons that content routing tends not to be able to influence the network. It's not really a question, that's just a comment.
Thanks. In fact, this is precisely the kind of comment that I was looking for, the kind of feedback that we wanted. So as I mentioned, AS path poisoning is really not the best way. So if you could find better methods, that would be perfect.
More questions?
Michael Sinatra, ESNet. I guess my question is, how close does this get us to actually doing content-centric networking, like what Jacobson and people like that are starting to do? And should we be putting our efforts into that instead of some hybrid solution like this?
So can I ask you for a clarification of what you mean by content-centric networking? I'm not very familiar with that.
I'm specifically talking about the work that Van Jacobson, I believe Alicia's involved in that also, and a few other people are doing on NDN and named data networking and content-centric networking. And how close are we to that project here? It would be nice to know a little bit more about what's going on in that project, but you know, I'm just wondering, at what point do we go all the way to doing something like that, as opposed to a hybrid thing like this?
Sure. Maybe I should talk to them and figure out the answer to that question. Thanks. Right. Thanks a lot.
Let's thank the speaker. Don't leave yet. Important announcements. We have winners from the survey yesterday. Chris Spears, is he in the room? Chris Spears. All right. You have a surprise gift waiting for you at the registration desk. So make sure you pick it up. A few announcements just before you guys head out for lunch. If you have an idea that you want to share with the rest of the group here, lightning talks is the best way to do that. Highly encourage you guys to submit a lightning talk and try to get your 10 minutes of fame or shame, depending on how well you do. No, I do encourage you guys to do it. Do fill in surveys. It's really important for us on the program to figure out what's working and what's not. So it takes a little bit of your time, but do that. If you are not a NANOG or a NUNOG member yet, make sure you can do that. Again, it's your way of supporting the community. Lunch is on your own today, and we reconvene at 2:30 for a talk by Randy Bush on RPKI. So that's it from this session. Have fun, guys, and see you in a bit.